So, I've picked up working on my Voron again, and tuning that machine has been going really well. At least until it didn't. Oh boy. Oh boy. Well, that's on me. I should have seen that coming. Good news, the toolhead is now as good as new, but the whole tuning process has got me thinking. Printing fast isn't just about, dialing in input shaping and cranking up the feed rates. To even get to that point, you're already building on so much other tech that each solved one piece of the puzzle along the way. So, what are the steps that got us here? And the first step is actually just getting the printer to have some control over what its motion systems are doing. If you remember the first popular 3D printers like the MakerBot Cupcake, those did have the same kind of stepper motors that we still use today on the X and Y axes. But for the Extruder, they used a pretty primitive geared DC motor that you would simply turn on and hope that you would get a somewhat constant feed rate for the entirety of the print. There was no precise control at all. In fact, this was a system that mostly relied on the components finding an equilibrium between themselves. Plastic gets harder to push through a hot end when you try to go faster, so that would slow down the motor, and vice versa. But because this was a system that runs itself, that one constant feed rate operating point was all it could do. So extruders moved to stepper motors as well, and now to brushless servos. Not because they have more power, but because we have finer control with them. That means we have more freedom and can better optimize the rest of the system that makes a 3D printer. And we can make use of more of the capabilities that the machine already had, but that we just couldn't access yet. One way that I thought of how I could visualize this idea is that if this is the entirety of a printer's capabilities as a whole system, some regions are straight up failures like skipped steps, others are bad print quality. We always want to be able to use as much of that capability space as possible. If the best our current control system can do is a square, then we're going to leave a ton of unused potential on the table. We could try to make that area that we can fit a square in as big as possible by just throwing more material at the problem, like extra rigidity, bigger motors, and fatter hot ends. But that gets real expensive real quick. Or we could make better use of the capabilities that the machine already has. And that comes in the form of more fine-grained software control, and nowadays even with some passive, active, and predictive compensation for the shortcomings of the mechanical systems we've got. Input shaping is fantastic, but it's just the tip of the iceberg, and honestly, it's not even a particularly advanced feature. But this doesn't mean that we can now just build machines from paper mache and slap some software on top that will fix it. If the hardware has a capability space that looks like this, no amount of software can improve that. Machines still need a base level of rigidity, so let's go over the hardware improvements. Actually, should this video have been a tier list? I've never done one of those, but I'm thinking that would be a good format for this because, we've got so many individual elements in play. Let me know in the comments below what you think after you've watched the video. So, hardware. You'll probably immediately go to bed slingers versus Core XY, which I think is just too much of an emotional debate. Core XY and other moving head systems like the Ultimaker Cross Gantry, H-Bots, and actually Deltas keep what is typically the heaviest part of a 3D printer stationary. And that is the heated bed, not the toolhead, the heated bed. Beds weren't always heated, so they weren't always as heavy as they are today. But it does make sense that we're trying to limit how much we have to fling them around these days. But on smaller printers, where the bed is physically smaller and doesn't weigh that much more than the toolhead itself, keeping the bed moving doesn't actually slow down your machine, because if your toolhead already has the same motion constraints because it's the same weight and uses the same motor, then by eliminating the bed, you're not really going to gain anything. And on a small printer, you're also not going to be printing massive parts that would tip over from the movement. But, technically, this is a bed slinger too. For a while, it was also looking like everyone was running to Bowden extruders to make the toolhead even lighter. But I think that actually ended up being a bit of a dead end. Sure, relocating the heavy stepper motor from the moving toolhead onto the stationary printer frame makes the moving toolhead lighter, but it also makes precise filament control a lot harder. That puts us in the same trade-off between building a system that has raw performance and building one that we can precisely control. Today, we're at a middle ground where the extruder is again part of the moving toolhead typically, but it's built as lightweight as possible with smaller motors and extra gearing. Bamboo now uses a BLDC servo, and Bowden setups have basically disappeared because it turns out that controlling for that little extra weight is more doable and has fewer downsides than compensating for the imprecision from the Bowden tube. Title: Software. And yes, of course, software is pulling a lot of the weight here. I mean, the core challenge is how do you move around something that has a non-neglectable amount of weight as quickly as possible, while also, at all times, positioning it to a degree of precision that isn't going to show up as artifacts in your prints. And at the same time, you also have to respect the capabilities of these stepper motors driving the whole thing. The most basic approach, and the one that was actually a surprisingly good fit for the DC motor filament extruder, was that you just don't worry about any of that. You run the machine slow and at a constant speed. Don't do any acceleration logic, and you just don't worry about resonances or any of the likes. All the controller knows is that over the next, say, 50 milliseconds, it has to send a specific number of pulses to the drivers of the X and Y axes. And because the printer is slow, direction changes are also mild enough where the elasticity in the system, belts, motors, the plywood frame at the time, will soften that impact enough so that, yeah, at the end of the print, you actually get a part out without doing any sort of advanced kinematics. But obviously, this is not a very elegant approach. One of the first improvements made was to introduce a constant force acceleration scheme. And basically, instead of having a sharp pulse where we demand an instantaneous direction change or reversal, that pulse is now spread out over some amount of time. But now you get a new problem. The toolpath that a 3D printer follows isn't smooth. The G-code is just straight lines, lots and lots of straight individual segments, and the only way that a printer with constant force acceleration can follow those segments is that it has to, fully ramp down and ramp up in speed for every single move as soon as there is a deviation in direction. Which also isn't great. So in the end, we got a compromise, and we now just have sort of a fudge factor that allows the printer to jump speeds within reason. That's junction deviation, or imprecisely called jerk. And that basic combination of a constant acceleration factor plus some instantaneous leeway served 3D printers pretty well for a pretty long time, until these Voron guys came along and messed everything up by wanting to go even faster. And you know what can make your projects faster? Using professionally made parts from today's sponsor, PCBWay. One of the harder lessons that I had to learn, and that I'm still struggling with, is that as a maker, you don't have to do every part of the process yourself for it to still be your project or your thing that you built. I know how interesting it seems to have your own CNC router, a pick and place, laser cutter, 3D printers, obviously. But for getting stuff done, you're just going to get a better final result and also save a bunch of time if you outsource the really specialized parts. And PCBWay does just that. The biggest revelation for me has been ordering populated SMD boards. They're so much nicer than soldering your own through-hole parts, and trying to get good at placing and reflowing SMD is a whole hobby by itself. PCBWay also offers CNC routing, milling, and turning, does 3D printing from standard and specialized materials, and even does sheet metal work, which is a pretty rare offering. If you value your time at all of these end up being cheaper than trying to figure it out yourself. So check out PCBWay as your project partner at the links below. And if you need some inspiration, check out their project sharing section at pcbway.com/project. Oh, and I just got an email. PCBWay are giving out 200 coupons for $10 off with this code. Do check them out. So, slicers. They still had to catch up. If you look at the heritage tree of slicers, it's almost like everything is related to everything. Even between the Slick 3R tree with Prusa Slicer, Bamboo Studio, Orca Slicer, and Super Slicer, and the monolith that is Cura, there's still a lively exchange of features and algorithms. The slicer is an offline process, so how fast that runs doesn't really matter. While it might be possible to print everything at the same leisurely speed when the motion system is holding you back anyway, slicers now can detect areas of your prints based on their function, like overhangs, bridges, or thin walls, where if you were going to use the same set of settings as for the rest of the print, that one area just would not print well. So instead of having to limit everything just to get that one edge case printed well, slicers now have pretty granular settings overrides and modifiers that apply only to those edge cases. And it goes down even deeper with today's slicers. The print path generation itself also optimizes for what type of moves will work best for a typical 3D printer system. For example, instead of filling in small sections with tiny back and forth lines that would take forever to complete and shake the printer while doing so, you now automatically get concentric infill just for that area, which is much faster and smoother, and because it's such a small area, you'll get functionally the same result. So I hope this was enough prep work to get you to see that printing fast isn't just one thing like, hey, let's check input shaping on here and it will be a beast. Input shaping is more or less just the final polish once you're already there, and it's lots and lots of tiny little improvements that got us here. But of course, 3D printer mainboards kept getting more and more compute, and with Clipper, they even have a whole Linux system available to them that does compute for them. And that is being used to, again, fit what the printer does better into what the platform is capable of. I think the simplest way to explain input shaping is that it's basically a frequency EQ for every move your printer does, with the job of reducing only the frequency range that your specific machine resonates at. Turns out, movement that uses basic acceleration ramps still behaves like a full spectrum shock to the system, and that excites any frequencies that the printer naturally rings at. Input shaping modifies those moves in a way that those critical frequencies are less present, so we're providing the motion system with less energy at those frequencies that it would otherwise resonate at. If you want to swing a pendulum, the only frequency that it cares about is its natural frequency, so we can get from A to B either in a way where we excite those frequencies or in a way where we excite them, well, a bit less. Now, this is, I guess, a bit of a passive resonance avoidance approach, unlike something like active noise cancelling from headphones, where the drivers actively introduce extra and new movements that work against those unwanted frequencies. Again, same thing here. If we have some resonance going on, we can introduce extra movement that stops that. Still, input shaping does a pretty good job reducing the ringing artifacts that you get at high speeds on sharp corners. I mean, the same sort of ringing artifacts also do exist at lower speeds, but higher speeds obviously introduce more energy into the printer, into the motion system and the frame from just having to accelerate and decelerate harder. And going faster also stretches out the wobbles on the outer walls so that you can actually see them. If you're printing slow, like all the wobbles will be gone by the time that the nozzle has moved a bit. Though not every input shaping implementation is identical. Depending on how they're tuned and how well designed the rest of the motion system is, it's not uncommon that you'll see smaller details in prints getting somewhat smoothed over. But either way, I think the difference just in how sophisticated a printer can sound by adding input shaping is pretty amazing. Listen for yourself. Now, pressure advance, this one actually is a much more active component. Hot ends don't react instantaneously to filament being fed in. Remember how slicers now do feature detection and constantly adjust parameters depending on what is being printed? Well, that just wouldn't work if the hot end would just keep oozing out filament at the wrong rate. So, especially when you go from a high flow rate situation to slower moves, the plastic flow through the nozzle essentially gets out of sync with the print moves. So pressure advance is a little predictive model that accounts for the hot end's delay and natural ramp up and ramp down, and it feeds it a little more or a little less filament in advance, hence the name, so that when that flow change gets to the nozzle, it's actually going to be in the right spot. This delay in hot end response is also why hot ends typically aren't designed with super long melt zones anymore, like this one or the E3D Super Volcano, if you remember that. That was pretty crazy. And nowadays, they instead use high flow nozzles, like the CHT or soon the E3D Fuge. Those keep the amount of squishy liquid filament small, so that you get a sharper response, but still maximize the contact area with the filament to introduce heat as efficiently as possible. Just like with input shaping, pressure advance can improve things, but if there's the option to just cause less of the issue in the first place, that usually is the better choice than trying to compensate for it afterwards. But there still is one pretty hard limit that I don't think we've entirely solved yet, and that is cooling. Sure, getting more heat into the filament and melting it faster is doable now, but that energy doesn't just disappear when the filament leaves the nozzle. And especially with printing PLA, you need to get the print cooled down pretty quickly or it's going to turn into a blobby mess. The solution right now is just to add, more airflow to the printer somehow with stronger fans on the toolhead or with extra fans off to the side. But I feel like we haven't quite found the right solution for this yet. Maybe, PLA will always just be limited by how much cooling we can apply, and faster prints are going to be something we do with PETG or ABS instead. We'll see. There are some promising newer techniques that would make movement even faster too. I mean, stepper drivers have been a huge part in running the stepper motors simply better, but it looks like we are, in fact, moving towards more of a servo drive setup. Bambu Lab already uses a BLDC servo in the toolhead, and I'm going to start experimenting with putting one of these on the XY Motion as well. On the Do It board that drives this Warren, you can also enable phase stepping, which reduces the internal resonances of the stepper motor. And maybe in the future we'll also see open loop or closed loop FOC control. Got a whole video about that. But basically, instead of turning a crank by just yanking straight towards the position you want it to be in, this would instead pull in the direction that gets you there the most efficiently. Because in the end, absolute speed is not the limiting factor. It's how quickly the machine can get to that speed and slow back down. And then how many print artifacts it will cause along the way. And almost all of the techniques I explained in this video are not about going faster per se, but about controlling those artifacts. And that brings me to the end of this video. Let me know if this should have been a tier list. As always, thank you all so much for your support. Take care of yourselves, keep on making, and I'll see you in the next one.